index theory, section 6.8 of Strogatz. What we've done before, looking near fixed points, linearizing near fixed points, is an example of a local method. And that gives us a detailed view of what trajectories are like in the neighborhood of a fixed point only. So that's what I mean by local, in this infinitesimally small neighborhood. But index theory is an example of a global method. It provides global information about the phase portrait. So it's not just limited to local things. Global just means not limited to a neighborhood, infinitesimally small region. And it tends to mean something related to a large chunk of phase space. That's what we mean by global. So this is compared with local info from linearization around fixed points. We'll be able to answer questions such as, must a closed trajectory, meaning a periodic orbit, always encircle a fixed point? If so, what types of fixed points are allowed? What type of fixed points can coalesce in bifurcations? So let me first just describe what it is. The idea is we have some vector field and we've defined a curve, a closed curve. And it's okay if it has sharp corners. It's not important that it has sharp corners. All that matters is that it's a closed loop. It does not have to be a trajectory of the system. In some sense, if you've taken a course on electrostatics, it's a bit like a Gaussian surface used in electrostatics, where you're trying to look at what some vector field is along that surface to infer the magnitudes of charges inside that surface. So it's a lot like that. So think of this as it's a curve, pretty arbitrary curve. It cannot include a fixed point. So you can't have a fixed point on the curve. So pick some test curve C. Does not have a fixed point on it. It is not necessarily a solution to the system, not a trajectory. So here's what we'll do. We're thinking of the situation where I'll write it in this vector way. X dot equals f of x. This is a two-dimensional vector field. We write x dot as vector x as x dot and y dot. So at any particular point, let's say this point, we've got a vector. So here's our vector. And it's got little x dot component and a y dot component. This angle that we'll call phi is important. So phi is the angle the vector makes with respect to the x-axis. The index of this curve C is that here I have a vector, and I don't have a closed curve, unfortunately. I guess I have this plate. So imagine this is the edge of a closed curve. I will look at how that vector changes as I go around my curve counterclockwise. As we move counterclockwise along the closed curve, we'll look at how this vector changes. So maybe it's up here, and then as we keep moving, and we're just sort of mentally moving, how does this vector change? What about here? So as we move counterclockwise, how many turns does that vector, the red vector here, make in a counterclockwise sense? So from what I've drawn right here, we could figure out what that is. But let me first, I'll write phi with a box around it, C, means it's the net change in that angle over one circuit, counterclockwise circuit of C. So this is going to be some integer multiple of 2 pi. We define the index of the closed curve C as I sub C equals 1 over 2 pi, and then this net change. So we're measuring the net change in the angle in terms of radians. So IC is the net number of counterclockwise revolutions made by the vector field as we move our point once counterclockwise around C. So for the example shown up here in red, how can we figure that out? Well, what we could do is label each of the points, say starting here, the one that I first showed on the right, maybe I'll label this 1, then 2, 3. So we're just going in order that we would going counterclockwise. 5, 6, and then this is also, we've gone back 7. Now take all those arrows and match them end to end. So the first one was up here. This was 1. And then we had this. Then we had this. The magnitudes don't matter, just the direction. And then this, 5, 6, and then back to 7. So if you go through that sequence, we turned around once counterclockwise. So that means this is 2 pi. We went around 2 pi. So the positive sense is counterclockwise, just like the way that we traversed it. So that means the index is +1, for example, above. For that closed curve and that vector field. What's this vector field sort of showing? It looks like all the arrows are sort of coming out, meaning if you were to kind of roll the movie backward in time, it seems like maybe there's a fixed point inside, an unstable fixed point. All right, so let's look at other examples just to get an idea of calculating this index, and then I'll say some things about the property of the index. So here's another example. And this one, I'll just plot some of the vectors. So let's say things are kind of going like that. And just pick a closed curve that passes through all of them. And then do what we did before. We could label them, maybe starting at the right and then going counterclockwise. So 1, 2, 3, 4, 5, 6. Then 1 and 7 are the same. And then line up things. So you kind of transport these vectors and just line them up. So here's 1, 2, then 3, 4, 5, 6, and then back to 1. And what did the arrow do? So the arrow goes around counterclockwise once. So the change for this particular case, if that was my curve C, the change is +2 pi. It went counterclockwise once again. So this is +1. But notice here, the arrows are pointing inward. They're pointing inward, which sort of suggests somewhere inside this closed curve, there may be a fixed point, and it's a stable fixed point. Everything's going in. So an unstable fixed point and a stable fixed point both have an index of +1. So let's try this again for yet another example, something like this, and then try to draw a closed curve that's going between all of these. There's a closed curve. You can make any closed curve. It doesn't have to be a circle, it's just a closed thing. So, okay, now if we use the same procedure as before, we start here on the right and then go counterclockwise. So just 1, 2, 3, 4, 5, 6, 7, 8, and then this is the same as 9. Parallel transport all of those and put them at the same point. So here is 1, 2. I'm just sort of lining them up so the tail of the arrows are all at the origin. And you can kind of see what's happening, right? This thing is already going clockwise, not counterclockwise, but clockwise. What about at 3? Okay, here's 3, here's 4, here's 5, 6, 7, 8, and then back to 1. So it looks like we did clockwise 1 turn. So that means the net change in the angle as we went around, now there's a negative sign, -2 pi. So the index of this is -1. In fact, you could come up with indices of any integer. You can cook up some set of vectors that you link them all with a closed curve, and you could get +2, -3. You can get 0. You might be wondering about that. What's 0? It should be clear here. All of these vectors are basically pointing in the same direction. There doesn't seem to be a turn. So there's no turn. as we go along that curve C in a counterclockwise direction. So that means the change in angle is 0. So the index is 0. And yeah, you could have other weird things. It doesn't have to look like this to be 0. Why not do another? Here, I'll explicitly write it. So if x dot equals x squared y, and y dot equals x squared minus y squared, then we could evaluate this vector field along some conveniently chosen points. And if we did that, let me just sketch what we would get. Here's x and y. At the point, for example, 1, 0, so here's x, y equals 1, 0. If we plug in that, what do we get? We get a vector that's pointing just straight up. And then if we pick other points, find it somewhere that's going that way. And then at 0, 1, so along the y-axis, we'll get an arrow pointing down. And then over here, we get something pointing again to the right. And over here, vector pointing up. Down here, something to the left. Then pointing down, and then pointing to the right. And we could link a closed curve between all of those. There's my closed curve. Doesn't have to be pretty. But if you then start labeling these like we've done, 1, 2, 3, this one's 4, 5, 6, 7, 8, and then back to 1. Put them end to end, we get, so this is 1, and then 2 is over here, and then 3. But then it seems to reverse course back to this direction, 4. So it looks like we went this way, and then now we're going back. In fact, 5, then 6, going this way, then 7. Oh, we made a full turn. Oh, but then we go back, because if you look at what's 8, 8 is pointing directly to the left. So we're turning back again, and then back to 1. So we actually did net 0 turns. If you look at what the number of turns was, we did a clockwise turn for 180 degrees, or in terms of radians, that'd be negative pi. And then we did a counterclockwise for a full 360. And then we did another clockwise turn, half a turn. So this is 0. So this curve has index 0, even though it's more interesting than this example up here. If you're curious, oh, what does this vector field look like? I've plotted it in that online phase plot portrait. So this is what things look like near the origin. It looks kind of weird. The right-hand side looks kind of like a saddle, but I don't know. So we've plotted some examples of getting the index for a curve, but we haven't yet talked about how this is useful. And so to talk about how it's useful, we need to talk about properties of the index. So let's say something about that. Property 1. You might be wondering, what if my closed curve is actually a trajectory of the system? So the index for a closed trajectory of the system is +1. If you think about it, let me draw just some random looking shape. For this to be a closed trajectory, that means at every point along the trajectory, the vector field is tangent to the trajectory, no matter how many twists and turns it does. And hopefully you can convince yourself, right, as we go around, the arrow, in this case, I've drawn a trajectory that goes around counterclockwise. And so, of course, the arrow must also go around once counterclockwise. The net amount is once. So for this particular case, we would get IC equals +1 for this closed curve. Now, if I reversed the arrows, so here's another thing, and maybe I'll draw the arrows going this way. And maybe it's easier to do it if we label it. This is a trajectory that's periodic, but it's going in the clockwise sense. However, for index theory, we need to traverse in the counterclockwise sense. So here is 1, 2, 3, 4, 5, 6, and back to 1. And this vector went around once in the counterclockwise sense. So it doesn't matter if the closed trajectory is going clockwise or counterclockwise. The index for a closed trajectory of the system is still 1. Which sort of naturally leads to another point, which is that if we reverse all the arrows in the vector field, and that's equivalent to changing t for negative t, it's like a symmetry, the index is unchanged. And what's the proof of this? All the angles go from phi to phi plus pi. They just change direction. But the net change in phi as you go around one circuit doesn't change. So this is why if you have all the arrows pointing inward or all the arrows pointing outward, right, that's just a difference in, it'd be like if you take the vector field, everything's flowing in, and now you reverse time. Oh, now everything's flowing out. Well, it won't change. So these two would be exactly the same if we have a curve that traverses it. That's why the examples above, the one that had things pointing in, seems like there's a stable point, and then the other one with maybe surrounding an unstable point, they both had index equal to +1. There's an additive property that these have, which is kind of interesting. So if we subdivide our curve C, so for example, here's a curve. If we were to subdivide it into two parts, so I'll call one of these, I'll just sort of split it in half, and one of these I'll call C1, and then the other one, I'll maybe make it maroon, but also dashed, C2. And we always have to traverse these in a counterclockwise way. Hopefully you can see there's something interesting in this bridge region where C1 and C2 connect. The vectors along there, they're traversed one way along C1 and then in another sense along C2. So they cancel out in the sense that it's sort of the union of these two curves, but hopefully it's understood if I were to write C equals C1 plus C2. So we've subdivided C into these two regions, two curves. The index of C is equal to the index of C1 plus the index of C2. If I plot the vector field along here, it doesn't really matter what it does, because in one sense it's traversed positive, the other it's traversed negative. So that region in the bridge is counted twice. So the contribution to the net change in that angle on the bridge, this is the bridge, right, where the two infinitesimally close to each other, is counted twice, once in a positive sense and then once in a negative sense, because you're traversing it two opposite ways. So they just cancel out, and that's why we have this property. Another property, and this is that if C can be continuously deformed, if we take the curve and continuously deform it into another curve without passing through a fixed point, then the indices of those two curves is the same. Then IC equals I of C prime. So if we have some curve C, and now just think of doing an infinitesimal movement to some other curve, maybe slightly inside of it, C prime. As long as we didn't pass through any fixed points, the values of the index will be the same. And the reason is we're assuming that the index, well, since we're continuously deforming the curve, that means the value of this function, the index function, must vary continuously. But since it only takes on integer values, if it changes any value ever, it's a discontinuous jump. An integer valued function, if it's continuous, it must be constant. And this is useful because we could shrink down curves to just surround a fixed point and then get the idea of an index for a fixed point. Here's another property. If C doesn't enclose any fixed points, then the index is 0. And it's a lot like an example I showed up above. Let's just pick a region where there's no fixed points, so the flow is just sort of doing its thing. There's no fixed points in there. The arrow, it looks like as we go around, we're not going to get any change in the vector. So that angle will not change at all. There are other ways to get index zeros. This doesn't go in both directions. It's just if C doesn't enclose fixed points, then IC equals 0, but it's not the other way. We could have IC equals 0, and yet there are fixed points. So because of this property 4, this one about continuously deforming, it makes sense to define the index of a fixed point. So for now, I'm done with properties. So due to that property 4 above, it makes sense to have the notion of the index of a fixed point. The index of the fixed point, and let me just give it a name, x star, would be the index of any closed curve that encloses that fixed point and no other fixed points. So if I have a fixed point, x star, and here's some really large closed curve, but I could also shrink it down to something that's really small and just includes that point. These would have the same index and be the same as the index of the point itself. So the index of a fixed point, the index of any closed curve that encloses x star and no other fixed points. And so we could, in some sense, drop the subscript c and speak of the index of that point. Maybe we would say, the index of that point, x star. We could then find what's the index of various fixed points that we've talked about, right? We've talked about stable nodes, stable spirals, unstable nodes, unstable spirals, centers. It's going to be a lot like things that we've already calculated above. So I could just summarize it for you. The index equals +1 for stable and unstable nodes and spirals and centers. The index equals -1 for saddles. So it sort of makes saddles stand out as a totally different kind of thing compared to these others. If we were to use the plot we had before for describing the fixed points in 2D, remember we had the delta was the determinant of the linearization matrix, and then tau was the trace. And I think before we divided things up over here for positive delta into stable and unstable. Well, now all we know is the index here is +1. And on the other side of delta equals 0. So delta equals 0, we don't have a well-defined index. So there's just this discontinuous movement from, we've got saddles and then everything else. So it's kind of interesting. What's up with saddles? And now let me give you a theorem. And this is a useful theorem. If a closed curve C encloses or surrounds, includes n, and they have to be isolated. That's the problem with the delta equals 0 up here. Those aren't isolated fixed points. It's like a whole continuum of fixed points. That's a problem. So if a closed curve C encloses n isolated fixed points, x1 star all the way to xn star, then the index of that curve is equal to the sum of the indices of the individual points. That's cool. The idea behind the proof is familiar if you've taken complex variables or electrostatics, where if you've got some closed curve, and let's say we've got a few fixed points in here. Well, you could deform this closed curve. Think of it as a balloon that you're shrinking down. You're sucking out most of the air, being careful to not hit the fixed points. So you shrink this down into something that will surround each fixed point, and then you've got these bridges to the other fixed points. I don't have very good memories of complex analysis, but that's right. We traverse this curve in a counterclockwise sense, and so this curve C can be deformed. So it's going to have the same index as this other curve that we'll call gamma, and so it must be traversing everything in the same sense. And like before, contributions due to bridges will cancel out, and all we'll be left with is, so if this was x1 star and so on, xn star, hopefully you could see what's going on. The index of this blue curve gamma is equal to the index of C. But the index of the blue curve gamma is going to equal the sum of the index of the points, because it's got these little bubbles around each point. And so that's it. That's the proof. So that's useful. Another useful thing is that any closed orbit has an index of +1. Here's another theorem. So if you just happen to choose a curve C that instead of being just some random curve is actually a trajectory. So now instead of saying closed curve, I'm going to say closed orbit. That means trajectory. And we do have to specify R2. Must close fixed points whose indices sum to the same as the closed orbit itself. And what's the proof of this? Well, you just use the theorem above and also the property of a closed orbit having an index of +1. That's it. You can use this to do things like prove that there are no closed orbits in a certain system, or that there will be closed orbits in a certain system. So as an example, I think we saw something like this, where I'll plot X and Y. We had a saddle point and then two centers. And so things were sort of going around like that, going around like that. We've seen a system that did this. Well, what if we took a closed curve? I'll draw some closed curve. That's also a trajectory. So this thing is periodic. Here's our curve C. So the index of C equals +1, since C is a closed orbit. It's a periodic trajectory. It goes back on itself. It's a solution to some ODE. In fact, if in particular in this case, I think it's x dot equals y, y dot equals x minus x cubed. This had a saddle point at the middle and then two centers. Well, what are the indices of each of these points? The index of this point, we'll label these just 1, 2, and 3. So the index of this has to be +1 because it's a center. The index of the saddle is -1. And the index of this other center is +1. Well, what do you know? Add those two together, I1 plus I2 plus I3, and you get +1. So it's true. Anytime you have a periodic orbit, because the index for that curve is +1, there has to be at least one fixed point inside, right? Think of what if I had chosen some other curve. I could go and do maybe green. I don't know if you'll be able to see it. But if this is also a closed curve, let's call this C prime. And so that's +1. And it encloses just one fixed point, which is a center. Now, what else could happen if we, sort of ignore that this is the system that happened? We're just thinking, okay, topologically, what could happen? If a fixed point disappears, we would need them disappearing in pairs. And then this is another thing where like the saddle node bifurcation emerges. You can imagine as we change some parameter that one of these center points will remain, but then the saddle and the center will merge. So we would get something, I don't know, that looks kind of weird, but it only has one point because the other 2 points had to merge. Saddle node bifurcation, the saddle and center merged. So this index theory seems kind of powerful. It gives some global topological view of what's possible, what can happen. You could also use it to figure out what for example, can't happen. So if you remember the example we had before of the rabbits versus the sheep system. So let me just put this down here. Can also prove there are no closed orbits, meaning no cycles. The rabbits versus sheep. And there, the phase space wasn't all of the xy plane. It was just where x is positive and y is positive. So the first quadrant. And if you remember what we had, there was an unstable point at the origin, and then there was a stable point on the y-axis, a stable point on the x-axis, and then a saddle point for here. And if we put the index, it's -1. So then you might ask, well, where could we possibly have a curve? What if we tried, could there be a periodic orbit here? Well, no, because this curve doesn't enclose any points. So the index of that curve is 0. What about, let's enclose one of the points. Can we have a curve that encloses this? Well, actually, no, we can't, because it hits the boundary of our space. So we can't have something that encloses it. At best, we could have a curve that has that fixed point on the boundary, but that's not allowed. So again, we can't do it. What if we had a closed curve that enclosed the saddle point? Well, that would give us an index of -1. So it just doesn't work. So there's no curve we can come up with. There's no curve, I mean, I guess we could say admissible curve that has index +1. So that means no closed orbits are allowed. So that could be pretty powerful. There can never be cycles in this system for the parameter values we showed. This is a predator-prey system, and predator-prey system famously does allow cycles if you change some parameters. But for this set of parameters, the system we studied is just not allowed.